Hello guys, welcome back to another little project that we got going here for microcontrollers. Today we are going to be playing with, this is actually a viewer request. We're going to be doing how to measure basically a voltage and display it on an LCD screen using the analog digital converter, as well as coding the LCD screen. So we're basically kind of combining a couple of things. If you want to review how LCD screens are programmed and whatnot, you can look at my LCD screen videos that I have, as well as ADC. There's an ADC video that I have, or at least a kind of a compilation of videos how to use the ADC. This one, what we're going to do is we're going to combine those two, plus I'm going to show you guys a little bit more in depth on the ADC for this one, since we'll want to be fairly precise with this. So we're going to be kind of looking at that too. For this, we're going to be using the PIC16F HV616. It's basically a lot like the 16F676 that we've been using. It's pretty much the same pin layout, same everything. It's a little bit of difference. I think memory stuff is a little different and whatnot. So there's some small differences, but for the most part, it's basically the same. So again, like I said, we'll be looking at the analog digital converter. Before I jump into this, let's check out the device overview. Okay, so this is that's the 10. That's not what we have. We have the 616. So 616. So here's our block diagram. We've got a couple of ports of six inputs each, looks like. We've also got the analog digital converter. Got a few timers here. Got the internal oscillator block, which we'll be using. Looks like we got the watchdog timers and all the other standard stuff. It's got 128 bytes of file registers, as well as it's got 2K by 14 program memory. So it's a pretty good little chip. So anyway, but we're going to be using this analog digital converter as was just our standard ports. What we're going to be doing is we're going to be putting the LCD bitwise data. We're going to be using the I can't remember what it's called. I just blanked. Basically, we're not going to use all 8 bits. We're going to use the LCD in 4-bit mode. That's the same way we've used our LCD in the last videos that I've done. So we'll be using 4-bit mode. So 4 of these will be locked up on the data bus for the LCD, and then the write and enable lines will be used in port A, as well as we'll set up the analog digital converter. And if you notice, we share a lot of pins, so we're going to be pretty much maxing this little chip out. We share a lot of pins. Let's see, 16, 16, okay. So we share pins, so A0 and AN0, AN1, AN2. Pretty much port A has all the analog digital stuff on it too. So we will be configuring and setting up port A for analog and digital inputs. So we'll be using the ADCON register, as well as some other stuff to set that all up and make sure that we get the right registers in the right places and whatnot, because we're going to have to tell it that one of these two of these pins for the LCD screen are going to be used as digital I/O, and then the rest can be analog, and we'll have to set all that up. So ought to be interesting. So let's go ahead and take a peek at the schematic here. Okay, switch that around and get the schematic up. So as usual, we got our normal, hello, I'm zooming crazy here. Got our normal power circuit here. We got our 12 volts in, our little decoupling caps, our 7805 voltage regulator, our 5 volts out, and then we're going to jump into this. And I've got actually some space for some other stuff. Let you kind of look at this and digest it here. Here's our LCD screen. Basically D0, D1, D2, and D3 is what I'm referring to as the data bus. It comes in to, it corresponds to D0 is going to be C0, D1 will be C1, and so on and so forth till you get up to D3, which is the 4th one. This is going to be the four bits of the data bus of this that we're going to be using for 4-bit mode. We're not going to use 8-bit mode just because a lot of people do this because it conserves pins. You have to have 8 pins. We don't have enough pins to do 8-bit mode. So when in that case you run this in 4-bit mode, and we'll see in the coding how you code this, just like, and it's going to be coded exactly the same as the LCD video that I did before. So I'm probably not going to run through the code as detailed as I did in the other one. Except I think we'll be programming this with high-tech C, so I may kind of pass through it fairly quickly. It's similar, I think the last one we did in CCSC, but it is similar, just a little bit different controls, but I'll pass through it fairly quickly on the coding section. But then we also have our RS, our read-write, and our enable pins, which is stands for, and so RS is for, I think, send or serial in. Trying to think, I don't remember. I'll have to look that up. Or send, I think it's send. RS is for send. E is for enable, and the read-write, that's the mode that it will be in. You can actually read characters from the screen, or you can write them, and then you can put it into where it accepts, what you tell it. So you can write to it. Now for us, we're just grounding that pin because that puts it into full write mode, because we're going to be doing nothing but writing out to this display. We're not going to be writing stuff out and then reading it back in, later. So that's and if you would ever need to do that, that's what that pin's for. But for us, for right now, we're just going to ground it because we don't need to read anything from this LCD screen. There's also this contrast pin, and where that's going is that's going over here to this volt divider right here. I'm just putting in a set voltage for it, basically. You can put in, most of the time what everybody does is puts kind of like over here, puts a potentiometer over here, or just a small trimmer or something, maybe around 10 to 20K, somewhere around in there, and you can play with the contrast and of the screen with that. And so what I've done is I found that I think this is fairly readable, fairly good, this 4.700K or 100 ohm, which that voltage that divider gives you, which I can't remember what that is right off the top of my head without calculating it, that gives a pretty good contrast to the screen. So you guys can play with that. That's another trick, is that almost every application that you see, there's usually a potentiometer on there, and you can put a fixed value in. That's okay. It's just most of the time most people like to be able to adjust the contrast, so you put a pot in there. So anyway, that's the contrast, and then of course we got our VCC and ground. That's pretty much it for the LCD. So we got the LCD all hooked up. Like I said, we got the RS and the RE pins coming over here to our AN0 and AN1, as well as the data bus over here on port C. I got our mem clear being pulled up. Now I'm going to get over into here. This is going to represent our voltage measurement. For right now, what I'm going to do is I'm going to just put a 20K potentiometer from 5 volts with a wiper connected to AN3, which is going to be our analog to digital port that we're connecting this to. What I wanted to also talk about is if you're going to actually be measuring voltages with this, and how to do that. What I did was I put a 0.01 or a 0.1 microfarad decoupling cap on this, just to make sure there's no noise. There could be some bounciness, some noise coming through here. So just to make sure that line's nice and clean, so it doesn't skew your results and the ADC get off. Also, I have no pop on this, which stands for no populate. I just wanted to show you that you can do this as well. What this is for, and I missed a junction. There should be a junction right here. Sorry, that actually is connected. If you guys see that, that's an oops. So that actually is connected right here. What that's for is that you've got these two resistors. This will be your scaling. So you will have to rate what your leads are going to be good for. So this is like your positive probe, and this is like your negative probe, let's say. What you will do, and then you put this across whatever you're trying to read, and it will this will scale it down to the 5 volts that this pin can take. So if it's like, I don't know, 0 to 30 volts or something like that, so if it's 30 volts, then you're going to look at taking figure out what kind of resistor divider you need to use to scale that 30 volts down to like 5 volts, and so that way you can, and then just to make sure and be safe, I put a 5.1 Zener that's right here in the middle of it too, so just in case for some reason something goes awry or you accidentally put it on, something that's 40 volt or something huge, and the scaling gets to where instead of it being 5 volts it's 8 volts or 10 volts going through here, this Zener will yank it to ground and only let 5.1 volts show up out here, so that's a good way. Now, a very big issue that I've seen with Zeners is be careful when selecting a Zener. Sometimes they tend to be very leaky. What I mean by leaky is they will actually, even though you're below their threshold, let's say you're 2.6 volts is what this line is seeing. These will rob current. Now it is microamps, but sometimes when you're dealing with, if you've got these two resistors because you don't want them to influence your measurement or steal too much current from whatever you're looking at, because when you're creating a meter, what you want is, oh, excuse me there, I had the phone ring. But anyway, what you want a meter to be doing is you want the you want it to be as big of an open circuit as you want, right? Because you're measuring open circuit voltage essentially. When you're measuring the voltage across something, so you want your voltage measurement, i.e., this little scale deal, to be as close to an open circuit as you want. So you're going to put probably mega ohm resistors in here, and that's why if you ever look at a meter, it'll tell you it's so many 100 mega ohm input impedance to the meter, or it's so many giga ohms. Well, that matters depending on what you're trying to measure, because you're basically putting 100 or 200 or whatever mega ohm resistor across whatever you're measuring, and so sometimes that can affect the circuit that you're measuring because it will rob microamps from it. Now the thing is that I'm talking about with the Zener is that you're robbing microamps through this, but then now you're going to rob even more microamps through this. Now the thing about these ADCs, and we'll see in a minute, is this ADC has its own input impedance too. So, or at least input impedance limit. It tells you there is a max, and I'll show you in the data sheet where that's at, that basically it has to have so much current, feeding into this to get an accurate measurement. Now it is microamps, but it's not a whole lot. So, but if you're playing in microamps and microamps and microamps, then any little bit could be significant. If this needs at least 10 microamps to operate properly, and you got 10 microamps through here, and then you're robbing another 20 microamps or something like that through this Zener because it's leaky, then you're going to throw this way off. You're stealing 30 microamps off this line, and so then now the voltage is going to sag. See, you're stealing too much current off of this, and so your voltage, instead of it being 2.5 volts, it might be 2.2 volts or 2.0 volts or something like that, which could really throw off, because the higher the voltage that you measure here and you're trying to scale it down to this 5 volts, well, you can tell in that scaling you're going to be way off if that moves in any little bit. You're talking millivolts represent maybe like volts out here. So if you're robbing any current and you're off, you're supposed to be 2.5 and you're 2.4, you could be like a whole 5 volts or something off out here, that you're trying to measure. You could be 5 or 6 volts off. So you want to make sure and keep track of your currents. See how big you're sizing these guys, and then look at the spec sheets on these protection diodes and make sure that you don't pick one that's really, really leaky, or that can and they'll tell you. The data sheet will have it in there. I may do a deal on diodes someday. I may do a deal on diodes and show you a data sheet, show you what to look for so far as their reverse current abilities and whatnot, because they do steal current a little bit. Most of the time, usually you've got a Zener on something, it's a signal line, so it doesn't really matter. You're looking for milliamps or something like that, and this guy's stealing microamps, so it's 1,000 times less than what you're looking for, so who cares? But in this situation, since everything you have to have, you're playing with really low current limits, because you don't want a whole lot of current being robbed, because otherwise that would affect your circuit that you're measuring. You don't want these resistors to be very small. You want them to be pretty large. And so be mindful of that. Be mindful and make sure you keep track of that with your Zeners and your other things. Make sure you don't pick something that's going to skew your results. In saying that, talking about what this guy needs, let's go back to its data sheet. If you go down here and on the side menu, you go down to Analog Digital Converter, which is section 9. It talks about the analog digital converter and how to configure it and all that fun stuff and all the buses. Well, if you keep scrolling all the way down, it even gives you a sample program. You keep scrolling all the way down past all the registers, how to configure it. It'll talk to you about the physical requirements. See, like the AD acquisition requirements. Okay, this is how you basically get the most bang for your buck out of this guy. It tells you about the whole law, but then it talks about right here in bold, it says the recommended maximum impedance for analog source is 10K. Now I'll show you what that means. They give you a little picture. They say see figure 9. So if you click on that, take you to it. And this basically from this point, from this X box with an X on, this is basically the inside. This is basically the inside of that of the ADC, of that pin, of that port. So here's the port, and this, what they've got in a box, this is your outside source. You've got some sort of voltage measurement that's coming in, and it's got some series resistance with it. It's talking about this this RS right here. This cannot be any larger than 10K, because that means that this guy, the impedance of this guy, he's going to suck so many amps out, and if you choke that down to where he doesn't have enough current to operate properly, then you're gonna skew your result. And as you can see, it's got what this is. A lot of people don't know what this is. This is input protection for ESD is what this is. So ESD, you know, can come from ground or positive. So they have this diode scheme, and basically if anything rises 0.6 volts above, you know, the threshold, it's going to conduct. So you've got, you know, this is your ESD protection. They're telling you right here that there's some leakage in this circuit. There's a 500 nanoamp leakage that's in the circuit. So basically, but due to whatever components or however the die is made or however the IC is actually made, it's got on this line, the minute you connect it to this analog digital converter, it'll rob 500 nanoamps from whatever you're connecting up here. Then it shows you that there's a sampling switch that's here, that's inside, and if for some reason that this series impedance is an issue, is something about, then they tell you what the sampling is. Okay, so essentially you got like basically two series elements, the one that's on the outside, that's yours, as well as the one on the inside, and they give you a curve for that. If you're running this at 5 volts, which we are, it's gonna be somewhere around what is that, maybe 7 kiloohms, something like that. And where all this comes into play is if you go up here, they give you an acquisition timing, how to calculate the timing, the value for TC approximated the following equations. And what this is if you look at it, this has half LSB error is used, and so which means that it basically rounds. It'll round on, and so your error that you have, it calculates. But it's basically about 1%. You got about 1%, give or take 1% error in sample. Is what it's telling you. And it's a little too complicated to explain here, but I may do that later. But you can just look up, just Google half LSB error, and you'll find tons of links, tons of stuff out there that explains exactly what that is and how to calculate it within your deal. But I won't explain it here because this is going to take too long. But basically what you're getting is you're going to get the acquisition time. See, when you take a sample, it takes so long for it to get an accurate measurement. You have to have a certain time interval. So if you're trying to create, you know, some sort of, like, let's say an acquisition system that takes samples really fast, like a sample a second or a sample every 50 milliseconds or something like that, where you're making kind of like an acquisition system, this all comes into play because it takes a certain amount of time for this to actually take a good accurate measurement and then be ready for the next measurement. And that's what you're calculating here. And so it shows you how to set all that up and calculate it all. But a lot of it is based off of what is that input impedance, because that will slow it down or speed it up depending, as well as input capacitance and all that junk. But for us, ours is really simple. We're not going for super precise. So what you would do, and then also your precision is these resistors too. That's another tolerance that's going to stack up on you. So watch your tolerance stacks, watch your currents, and also know that this is about 1%, roughly about 1% error. So whatever you're measuring, if it's 2.5, you're going to have a 1% one way or the other. So you may have 2.51 or 2.5 or 2.49. You're going to have somewhere around in there. You have a little leeway there. Also, you have these guys, and these guys could be these. If you're using 1% parts, then you got 1%. So now you have 2, maybe 3% that you're off. That potential for 3% variation in your stuff. If you want to make the accuracy higher, there might be, I can't remember, there's some things you can fiddle with on this guy to get it up a little bit more, but I think that half LSB error is pretty set in stone. It's pretty much a 1% deal right here. But out here you could change these to 0.5% or maybe 0.1% or 0.01%. You can go up in these tolerance values out here, and that'll relieve you and get you back to maybe where you just have an overall 1% error. So stuff to play with when you're actually creating like an actual meter type of a thing. And so basically what I would do is I would choose this guy's going to be your RS. Basically, let's scroll back down here. The series impedance, this is going to be your series impedance. So you're going to set this guy at like 10K, and then set this guy whatever the scale factor like needs to be. Something similar to that kind of effect. That way, the input impedance from the voltage that you're measuring can be no larger than 10K. Let's go ahead and go to the max, because if you're creating like a meter, then you're going to want the maximum allowable resistance in your circuit for your measurement. So that way you're not robbing a whole ton of current. And if you're in kilo ohms, you're around microamps. So ideally it would be great if you could do mega ohms, because then you're around nanoamps, and well, most of the time you rob 10, 15 nanoamps from something. Even 100 nanoamps from something, it's not really going to matter. But since we're limited by the internal impedance of the ADC, we got to use kilo ohms, and so be mindful of that. Know that you're going to rob some microamps from whatever it is that you're measuring. So anyway, that's basically it for the hardware portion. Hopefully that wasn't too super confusing. Like I said, what we're going to do is we're not going to populate these fixed resistors. We're not going to create a meter. I could do it later if you guys want me to do it later and demonstrate that. Shoot me some comments. If I get enough of them, I may go ahead and we'll do that. We'll change this around and we'll put resistors in, and I'll show you how you can create your own kind of meter type thing. In fact, I may just go ahead and do that. But you'll create your own like little multimeter using this. But for right now, first we're just going to use a potentiometer, because that way I can take and twist it around and I can show you that the voltage will change on the LCD screen due to the code on this. So that's pretty much it. I know it's kind of taken a while, but I wanted to kind of explain some of that precision stuff as well as protection, and kind of some pitfalls that you can come into putting together, trying to get accuracy. Try to squeeze every bit of accuracy out of it as you can. For me, if I was going to design a good digital meter, I probably wouldn't use the ADC that's embedded in one of these guys. I haven't seen any of the ADCs, what kind of error and whatnot that they have that are in like the 18F series, something like that. Or you can just get an external ADC, and those you can get them with, they have their own external clocks. So their sampling time is huge, so you get a really good, or not sampling time, but sampling rate is really huge, so you get a really good depiction of what you're trying to measure. Plus they also have way less error. You can get them down to almost 0.5% error. I bet you there's some out there, if you want to pay the money, that are probably like 0.01% error and stuff like that. So you can get it to where it's super precise. And then they may have different input impedances. And in fact, even just the 1% right here, if you're 1% off, I mean, that's not too bad. You're accurate up to tens of millivolts. So that's pretty good. But if out here, you could get to where you're not, these aren't K, you could get them, push them way up to mega ohms, then you could do really good. So you could find an external ADC that maybe has a maximum input impedance of of a mega ohm or 100 mega ohm or something like that, and then you can put that out here to gain your precision back. So just stuff to play with your precision. But for right now, I think the max we can squeeze out of this guy is you would do like a 10K here and just use K ohms. But then, like I said, watch that zener if you're going to put a protection zener in there. Really look close at their data sheets, and they'll tell you what kind of leakages that you'll expect out of it. And then if they don't, I mean, just try it and see what kind of leakages. Put like a little resistor in here or something you can measure, on the outside. Get it with a real meter, with like a good digital meter. Measure, that the voltage across that resistor and see what kind of current is flowing through here, and then see if the data sheet won't tell you, just experiment with it. So that's basically it for the hardware layout. I know that got lengthy, guys, sorry about that, but as always, questions, comments, anything that you need, let me know, drop me a line. I'll be happy to answer any questions that you have. Next will be the software. I'm not going to be able to get to software probably this week. I would like to get to where I release a video, at least, or some videos, every week. I know I missed last week, but I'm going to try to kind of keep that within every week to 2 weeks. I'll try to release maybe some new videos for y'all until I run out of ideas. So I'm open for ideas. Anybody else has any ideas? Like I said, this one's a viewer requested deal. So if any of you guys have anything else that you want to add, or any projects or things that you do, now I will tell you this, I won't do your project for you. Those of you that might be in college or something, I'm not going to do your work for you, but I will help you out if there's a specific thing that's a specific interface or something that you're having trouble with that may make a good video for lots of people having trouble with that. Definitely shoot me a line and let me know. I'll give you the basics, but it's up to you to figure out the whole system that you're designing. So don't ask me to design your stuff for you, but if you have trouble with a certain piece or part, definitely drop me a line. I'll be more than happy to see if I can't clear that up for you. So take care, guys. As always, keep coding, keep building, and above all, have fun with it all. Okay, we'll see you.